Now, given a pre-trained model, we generally start with prompt engineering and try to understand how the model works. But soon, there'll be situations when we'll actually have to do some fine-tuning. So in this video, I'll be diving into an example where we actually have to do some fine-tuning, and I'll be doing fine-tuning using the Databricks 15K dataset. I will walk you through how I created a mini dataset that's derived from this Databricks 15K dataset, and the model that I'm going to be fine-tuning is the Gemma 2 billion parameter model. I'll be fine-tuning on the Google Colab so that anyone with just a Gmail account should be able to fine-tune this model and then get their own fine-tuned model and look at the working of this model. I will also show the plots of the training loss to see how the loss exponentially decreases as the training progresses. I've just fine-tuned on 1,000 samples, but if you really want to fine-tune and play around with the model, then you can actually fine-tune on the entire dataset. I've uploaded the dataset on the HuggingFace hub and I've made it available publicly. So the notebook for fine-tuning is also available for free and can be accessed through the link in the description below. So without further ado, let's get started. So let's start with the preliminaries, which is to install the needed packages. We obviously need the transformers library from HuggingFace and the datasets library. So one thing I noticed with the Gemma model is that we actually have to upgrade these libraries, because in the default version of the transformers library that's available with Google Colab, the Gemma model and the Gemma tokenizer is not actually available. So we will have to upgrade them in order to make use of the Gemma model. Because we are going to be doing fine-tuning on a single GPU on the Colab, which is the T4 14 GB GPU, we actually need to make use of these libraries, which are PEFT, TRL, bits and bytes, and accelerate. And we also need the tensor board to sort of visualize the results of our training. We also need the JSON-L library, which we'll be using to sort of dump the dataset that we're going to create and then export it and then save it in the HuggingFace datasets. So we also have to log into the HuggingFace ecosystem, which we can do using the notebook login function available from the HuggingFace hub. So once we have logged in and once we have imported the packages, we can try to run inference on the Gemma model. As a first step, we can load the model and the tokenizer and then visualize the model architecture, and then finally run a query, which is a prompt through the pre-trained model in order to understand how the model responds. So here's the model name that I've given, which is Gemma 2. Then I'm just loading the model using the auto model for causal LLM. And I'm again loading the tokenizer using auto tokenizer. Beauty of auto tokenizer is based on the model name, it loads the tokenizer corresponding to that model. We don't have to worry about which tokenizer gets loaded. It's taken care of by the auto tokenizer class. Once we have the model and the tokenizer loaded, we can then print the model architecture to see what are the different layers that we can use for parameter efficient fine-tuning. So we can see that the Gemma attention layer has the query, key, values, and O. So these are the four main matrices that will actually be a fine-tuning when we do the parameter efficient fine-tuning. So to query the model, I've just written a query, which is, what should I do on a trip to Europe? And the model responds by saying, the answer to this question is not as simple as it seems. There are many different things to see and do in Europe, and it can be difficult to know where to start. If you're planning for a trip to Europe, here are some tips to help you get started. To begin with, it says, decide what you want to see or do. There are so many amazing places to see and do in Europe. Now, as an additional example, I've also prompted this question, which is, explain the process of photosynthesis in a way that a child could understand. And the response I'm getting is a little bit of gibberish. A 100-watt light bulb is plugged into the standard blah blah blah, which I don't quite get. Anyway, let's find out what happens with the fine-tune model. Before that, what I'm trying to do is, so just to motivate for parameter efficient fine-tuning, what I'm trying to do here is to load a dataset and then initialize the trainer and then start the training without doing any parameter efficient fine-tuning at all, and then find out what really happens. So in this case, I'm going to use the Databricks-dolly-15 dataset. So the dataset is a corpus of 15,000 records generated by thousands of Databricks employees to enable LLMs to exhibit the magical interactivity of ChatGPT. So Databricks-dolly-15 is an open source dataset of instruction following records generated by thousands of Databricks employees in several of the behavioral categories outlined in InstructGPT paper, including brainstorming, classification, closed question answering, generation, information extraction, open question answering, and summarization. So we can happily use this dataset. So let's switch to our code and see what we can do. So what I'm trying to do here is just load the dataset, and I'm just taking the training split of the dataset, and from that I'm just going to use the first 1,000 records, and I'm just trying to visualize the first record and then see what the instruction is and what the corresponding response is to understand how the data looks. For example, the instruction is, when did Virgin Australia start operating? And the response is, Virgin Australia commenced services on 31st August 2000 as Virgin Blue with 2 aircrafts on a single route. So this is just one record. And if you want to get a detailed look of the different records, we could just browse the HuggingFace dataset card, or we can switch to the viewer and then look at quite a few records there. We can see there are some instructions with context and there are some instructions without context. And there are also categories which says closed question answering, open question answering, classification, information extraction. So we can use the dataset for quite a few fine-tuning tasks. So what I'm trying to do here is just kind of format the prompt and then initialize the trainer without actually doing any sort of parameter efficient fine-tuning. And then I'm just trying to start the training using trainer.train. As expected, we are getting a CUDA out of memory error because a 14 GB GPU is simply not sufficient to fine-tune a model that is like 2 billion parameters. So what we'll have to do is resort to parameter efficient fine-tuning. And in parameter efficient fine-tuning, I'll be creating a new data set, and then I'll be visualizing the data set. And I'll also be doing a little bit of cleaning and pre-processing. And finally, I'll be uploading the created data set into the HuggingFace hub. And as a last step, I'll be using this data set to fine-tune the Gemma 2 billion parameter model. So to create my own data set, I don't have any in-house data. So I'm going to use the Databricks-dolly-15 dataset that's available, but I'm going to modify it. I'm going to create a mini dataset, which I'm going to use for fine-tuning. So for that, I've just loaded the dataset fully, the entire training split of the dataset. And what I'm trying to do is first get a count of the different categories. For example, open question answering, there are 3,742 records. For information extraction, there are 1,506 records, so on and so forth, to make the 15,000 records in the Dolly dataset. So to create the mini dataset, what I'm trying to do is I'm trying to filter out those records that actually do not have a context. In order to do that, I've just put a small condition which says that if there is some context, then continue without adding it to my list of filtered data. And if there is actually no context, then I'm going to format the data that is very specific to Gemma. For example, the Gemma model likes the input to be format as instruction, and next line, the data instruction. And again, after 2 lines, there has to be a response, and a new line followed by the response. So we need to stick to this format that is specific to the model that we are going to be fine-tuning. In this case, I've written a few lines of code just to format the data. And if you just look at a couple of records after we have formatted this way, we can see that the first record is, which is a species of fish, taupe or rope? And the response is taupe. And the second record is, why can camels survive for long without water? And the response is camels use the fat in their humps to keep them filled with energy and hydration for long periods of time. So those are the couple of records that are there in the filtered dataset. And finally, with this dataset, I'm creating a small JSON-L file using the JSON lines library that we just installed in the Colab. And I'm just writing the entire data dump into this JSON-L file. And if you go to HuggingFace Hub, I'm just creating a new dataset. If we go under new and then do dataset, we can give a new name and probably give a license and then create a new dataset. I've already done that and created a dataset by the name Databricks-mini. We can see that the data that we visualize there, for example, which is a species of fish, taupe or rope, response is taupe. One thing to note is that the format of this one is quite different from the actual DALL-E dataset. For example, the DALL-E dataset has 4 features, which is instruction, context, response, and category. But in our case, we have just one feature, and I've named that text. And under that, each record is just one single line of text, and everything combined together, both the instruction and the response are just combined together in one line of text rather than having both of them as separate features. So once we have got the dataset sorted, I'm loading the dataset again into the datasets variable, and I'm just taking 1,000 samples from the training record just to demonstrate the fine-tuning process. The next step in the fine-tuning process is to define the different parameters. So the first one we'll be defining is the LoRA parameters. And the next one is a bits and bytes parameter. And the third one is training arguments themselves. And finally, we'll be defining the supervised fine-tuning parameters. We're given a new model name, which is the Gemma FT for fine-tuning. For the LoRA, we'll have to define 3 main parameters, which is the rank. And the next one is alpha. And the next one is the dropout probability for the different LoRA layers. Basically, if you have sufficient memory in your GPU, you can have the rank higher, probably 64 or 32. To make the fine-tuning process easier and to make it consume less memory, I've reduced the LoRa R to 4 instead of 64, and I've left the other parameters intact. When it comes to bits and bytes, so we have chosen to use a 4 bits precision as the base model. Data type for the 4 bits is float 16, and the quantization type is NF4 instead of floating point 4. We have also disabled the nested quantization. If you have watched my previous video on QLoRa, you will understand that there are 2 stages, which is the standard quantization and there's double quantization. So this is the variable to enable or disable the double quantization. And then finally, we'll have to define the training arguments themselves. So you'll have to provide an output directory where all the training logs are created so that you can visualize the different training parameters later on. So, and the number of epochs, I'm just running it for 1 epoch, which is just going through the entire training dataset once. So we'll be choosing whether it's going to be FP16 or BF16. That entirely depends on the hardware. So if we check the device compatibility of your GPU, and if we get a major version that's more than 8, we can then set it to BF16. Otherwise, we'll be setting BF16 to false. So batch size, again, batch size can be varied depending on the hardware that you've got. So I started with a batch size of 16, and I realized that it was running out of memory, so I reduced it to 2 or 4. You can choose a batch size that suits your hardware. For example, if you have a cluster of 4 GPUs, then you could just increase the batch size, and the transformers library will take care of just scaling the processing. These are all the standard parameters like the learning rate, weight decay, which comes with the standard training of any neural network. I haven't changed any of these. I'm just going to leave these as such. So the max steps goes along with the epochs, the training epochs. if we are going to set the training epochs, then we probably don't have to worry about the max steps. I'm the kind of person who chooses the epochs rather than the steps. So I've gone for setting the number of epochs, and then I've set this to -1, which means I'm not bothered about the max steps. The next thing that concerned me was the max sequence length. So if we set this to quite a high number, let's say 128, again, we should make sure that we have enough compute in order to cope with this sequence length. So I played around with the sequence length for a bit before I arrived at the sequence length of 40. Now, if you have a cluster of like 4 GPUs or 8 GPUs, then you could feel free to increase the max sequence length to all the way to 56 or even higher. I'm going to leave it to 40, which was sufficient for my training. And I've set the packaging to true because we have multiple short examples in the same input sequence to increase the efficiency. So we want the training to be more efficient. So I've set the packaging to true. And when it comes to device map, so I was initially training on my local desktop, which has 2 GPUs. So I had to change the device map to auto, which ensures that the training makes use of both the GPUs. But if you have only one GPU, then you can probably go for device map to 0, which is the only GPU that's available to you. For loading the quantized model, we need to set some configurations to the bits and bytes library. For example, we need to create a configuration for bits and bytes, and we need to ask it to use 4-bit model in 4-bit precision rather than the actual precision that the model comes with. And we also have to ask it to use normal float 4. And we'll also have to use nested quant. We just saw that we're not using nested quant, but we need to specify that we're actually not going to be using a nested quant or double quant, basically. So once we have created those configurations, we now need to load the model, load the tokenizer, and then pass this configuration to the model we are creating. The token is to say that we actually have access. This is your HuggingFace token, which ensures that you have access to the model that you're actually using. And this is the bits and bytes configuration that I've just created. And the device map is auto to make sure that you're making use of all the GPUs that are available at your disposal. And finally, we don't want to be using any cache, so we are just setting it to false. And again, we're just loading the tokenizer, and we need to specify what the pad token is, the end of sequence or end of sentence token is. And we'll also be fixing any overflow issues by just setting this padding side to right. So moving on to LoRa configuration. As we saw before, LoRa has these parameters, which is alpha, the dropout, and the rank. So we need to specify those parameters in the LoRa config in order to initiate the parameter efficient fine tuning. On top of that, the most important bit is the target modules. Now, if you had watched my LoRa video, you'd have realized that there are only a few modules, especially the attention modules, that will actually be fine-tuning and will be ignoring the rest of the modules. So we need to specify the attention modules here, which are the target modules for fine-tuning your model. So usually these are the kind of modules that will actually be fine-tuning when it comes to LoRa. So after setting all the LoRa configuration, we now have to initiate the training arguments. So all those, the training epochs, the output directory for logging, and the batch size, and all those training settings will be passed to the training arguments class, and we'll be creating the training arguments. So now we have the training arguments. We could just print that to see what the training is going to use. For example, we have only one GPU, so the NGPU is 1. And these are all, for example, the Atom beta for the Atom optimizer, the epsilon for the Atom optimizer. So once we have those training arguments, we will be passing the model that we will be fine-tuning to the supervised fine-tuning trainer class, and we'll also be passing the dataset that we just created and uploaded to the HuggingFace hub. Remember, it's the
Databricks-mini dataset that we just created. And we'll also be passing the parameter efficient fine-tuning configuration, the list of configurations that we just created. And we'll also be passing the sequence length that we have defined. I chose 40, but we can choose 128 or even higher based on the compute that's available at your disposal. We'll be passing the tokenizer, the arguments, and finally we'll be initiating the trainer. So once the trainer object is successfully created, it's all about kickstarting the training by invoking trainer.train. So I let this run for one epoch, and that was 1340 iterations. And these are the training losses that were just logged during the training process. By the first look, we can see that the training loss has exponentially gone down, starting from 5.2 to all the way to 2.9, and then going down to 2.7. And what we can do is visualize the training in the TensorBoard. So for this, we'll have to just run this TensorBoard command, and then this TensorBoard visualization opens up, and we can see that the training loss has actually gone down, which is a nice thing. But at times, the loss goes up after a certain point in time, indicating overfitting. So we need to be wary of that. So if it shows any signs of overfitting, then we could resort to either augmentation, or we could sort of resort to adding more data points to your training data set. I just fine-tuned with 1,000 records, and so it's quite possible that the model has overfit the fine-tuning data. Let's find out by just querying what's going on with the fine-tuned model. So for prompting the newly fine-tuned model, I'm using the same prompt that we used for the pre-trained model, which is what should I do on a trip to Europe? Because we have fine-tuned only the LoRA layers, we need to be merging the base model along with the adapter layers that are actually being fine-tuned. So for this, we will be using the PEFT model class from fine-tuned, and we'll be merging the base model along with the new model that we have created. And this gives our fine-tuned model. And we also need to invoke the merge and unload function in order to arrive at the merged model. So once we have this merged model, we could pass the prompt that we just have on our hand, and then find out what's going on with the response. The response I'm getting is there are many things you can do on a trip to Europe. You can visit Eiffel Tower in Paris, the Colosseum in Rome, the Vatican in Rome, and the response is quite specific actually, but there's this response which keeps repeating the Pantheon in Rome, the Pantheon in Rome. So this kind of makes me feel that the model has a little bit overfitted. So it's time to go back, add more records to your training data set, and then rerun the fine-tuning and see the response you're getting is any good.
So we can keep playing around between training, evaluation, and testing, and we can just keep going on and on, training more models, and we can also keep changing the data or updating the data, and we can add more augmentations and again train another round to compare the trained models. So all this we can do when we can actually evaluate the results of the model. So in my next video, we will have a look at how we can evaluate these trained models. And we will also have a look at how we can quantize the pre-trained models or the fine-tuned models, so that we could just squeeze or compress these models, and then we could deploy them for production use. So please stay tuned for that, and I will see you in my next video. Until then, take care.